Check it out now, y'all.
NanoHub U, online instruction.
Hi again. We're back and we're starting a new week of lectures, and basically the topic for this week is going to be discussing how we can use concepts in statistics, which is what we reviewed last week, how we can use those concepts to describe the behavior of a collection of n particles, where n is a really big number. So we're not talking about n of 1,000 or 1,000,000. We're talking about n on the order of 10 to the 20 to 10 to the 23. So that's sort of the overlying theme of the next week or two of worth of lectures. There's going to be two reoccurring themes in these lectures. One is we're going to always be focused on the behavior of n particles, right, where n is a large number. And then towards the end of the second week of these back-to-back weeks of lectures, we're going to play off on this classical versus quantum statistical scenario. So the idea is pretty simple. If you've got classical particles in a box, each particle is well defined and you can enumerate it, you can count it. If instead those particles are replaced by quantum particles, where the quantum particle is now described by a de Broglie wavelength, right, it becomes virtually impossible to count the individual particles. The wave functions all become entangled and overlapped. And so, as a consequence, there's different statistics that have to be derived and applied to that situation. So these, if you're looking for an overall view of what's coming, these are the two themes that you'll see over and over again for the next 2 weeks. I always find it remarkable that historically science learned to deal with the properties of an enormous number of particles before it really discovered how an individual atom works. And of course, this is a tribute to the early workers in the field of thermodynamics. And what we now know why this approach worked is because the thermodynamic variables like pressure and temperature really are average values of certain quantities over a large number of particles n. And n, of course, is a really large number. It's not like 1,000,000, it's like 10 to the 23. So because n is so large, the average value of something that you would calculate, if it's just based on random chance, for small n, that number can, the average value of a number can fluctuate depending on how many trials you conduct. But as n gets very large, right, the random chance goes to virtual certainty. You get well-defined quantities, and these well-defined quantities can then be accurately measured. And these well-defined quantities are things like pressure and temperature, for instance, for an average gas, for an ideal gas. So to try and illustrate this approach, I like to just quickly review the kinetic theory of an ideal gas. You've probably seen this derivation at least once in an earlier version of a physics or a chemistry course. And it's worth to just quickly go through it and remind you of some of the principles. What I hope you'll take away from this discussion is not the details that are involved, but the overall simplicity and the realization that a lot of these macroscopic laws are really founded in the microscopic behavior of individual gas molecules and atoms. So that's the one overriding or overarching theme that you'll hear presented in this particular lecture. So to begin with, I like to just study one gas molecule, and I like to confine, so here's one gas molecule. I like to confine that gas molecule into a very skinny, tiny diameter tube, such that the gas molecule can just bounce up and back in one dimension. We'll call the dimension of motion y, just to give it a variable. And this cylinder that the gas molecule is trapped in is equipped with a movable piston. And the area of this movable piston we're going to designate by the letter capital A. So the gas molecule is only going to have a momentum, or only going to have a velocity in the y direction. The gas molecule is going to have a mass m. The length of this cavity, the length of this cylinder is going to be L. No other gas molecules in the cylinder whatsoever. And what we want to do is we want to actually calculate what force this gas molecule exerts on this piston, right? Because this would be the pressure, the effective pressure of this one-dimensional motion of a gas atom. So it's kind of a simplistic model, but it gets across a lot of the fundamental ideas in a very clear way. So one really important parameter is the round-trip transit time for this gas atom, right? In other words, how long does it take for the gas atom to go from the bottom up to the top, bounce elastically from this top piston and rebound and come back down again to where it began? Well, that time interval we're going to designate by this variable script delta times t, so delta t. And of course that distance, or that time, is going to be the distance traveled divided by the velocity of the particle. So if the particle has a velocity v sub y and the particle goes up and back, right, the length is going to be just 2L, where L is the length or the height of this cylinder. So this is going to be the round-trip transit time for the gas atom to bounce up and back. We also want to know what force this gas atom exerts on the piston when it rebounds from the piston. And to calculate that force, we have to calculate an impulsive force. This is something that we discussed in the first week of lectures. The force can always be represented as a change in momentum divided by the time interval delta t over which that change in momentum occurred. So for an elastic collision of this gas molecule with this piston, right, that means the momentum before the collision is equal to the momentum after the collision. The change in the momentum of the molecule is just the final momentum after the collision minus the initial momentum before the collision. There's a net negative sign that comes in because after the collision the molecule is going in a negative y direction. So the change in the momentum of the molecule is just minus 2 times the mass m times the magnitude of the velocity v sub y that molecule has. And then by Newton's third law, right, you say that there has to be an equal but opposite force exerted on the piston, right? So if the molecule has a change in momentum, then the piston also has to have a change in momentum, but the direction of that change in momentum of the piston is going to be opposite but equal to the change in the momentum of the molecule. So the change in the momentum of the piston basically gets rid of that negative sign because you have to introduce this minus sign as a consequence of Newton's third law. Okay? If you want to calculate the force that the piston feels, you have to divide by the time interval delta t that this molecule interacts with the piston. So qualitatively, what would the force look like if you could just measure the impulse force on that piston? Well, what you would see is a sequence of force pulses, right? The force pulses would be separated one from another by this transit time, script delta t, that we've defined. And there's going to be some interaction time indicated by capital delta t, right? This interaction time is schematically shown on this diagram. And it's not clear what to use for this interaction time, so it's not clear what we want to divide this change in momentum with, right? So it's not clear what quantity we should use in capital delta t for this impulsive force equation. So the way to get around that is to ask what's the average force acting on the piston, and right, the average force acting on the piston is going to be some number down that I've indicated schematically by this dashed line. And this average force is going to be constant over time, and it's going to be certainly less than the peak force that's been exerted on the piston. It's going to be greater than zero, right? So what we want to do is we want to calculate what that average force is. And that's done in the next slide. We do it by approximating these pulses that I schematically drew in the previous slide. We represent those pulses as well-defined rectangular spikes with a well-defined width and time, capital delta T. Our transit time, script delta T, is still the time interval between these individual pulses. And what should be apparent is if you wait for a time capital T, right, you're going to get, let's say, n of these pulses that occur. And the number of pulses that you get is going to depend on the time interval capital T that you wait. So if you want to calculate the average force, what you want to do is you want to measure the force at many, many values of time, right? And for each value of time, you want to record the force that results at that point in time. So if you divide this time axis capital T up into, let's say, k intervals, then you would have to sum the forces that you measure at each point k, and then you would eventually have to divide by 1 over k to get an average value. And that operationally would then define the average force acting on the piston. So, you can simplify this sum by realizing that most of the time intervals, most of the instants in time that you measure the force, you're going to get zero, because the force is essentially zero at all these time intervals between the round-trip transit times. The only time you're going to get a non-zero value for the force is if you measure the force at one of these peak values. So that allows you to simplify this sum over k measurements, right, as just the ratio of delta T, that's the time that the force acts, divided by this total time, capital T. And if we've got n pulses, each pulse is of width delta T, right, we're going to make a measurement, and we're going to measure F0 at n delta T time divided by the total time of the measurement, capital T. And so once you realize this sum can be approximated by this formula, then you can start to arrange the algebra to get an answer that makes sense. So for instance, if you divide capital T by n, you get this denominator. Capital T divided by n turns out to be just the round-trip transit time. The force F0 is just a change in momentum divided by the time delta T over which that change in momentum occurs. Of course, it's very difficult to know what delta T is, right? But it cancels out because of the way this argument is constructed. And at the end of the day, what you find is that the average force exerted on that piston by this molecule that's bouncing up and down, right, is just the change in the momentum of the molecule divided by the round-trip transit time of that molecule. So it's a rather simple result. And what we can then do is we've got an expression for both the numerator and the denominator in this expression for the average force. The numerator we calculated on a previous slide was just two times the mass of the gas atom times the magnitude of the velocity of the gas atom. This round-trip transit time is just 2 times the length of the cylinder divided by the velocity v sub y. And when we work out that algebra, we get something that looks like mv squared divided by L. By definition, the pressure that one molecule exerts on the piston, that pressure for one molecule is just going to be this average force, F average, divided by the cross-sectional area A of that piston. When you substitute in this expression for the average force, what you find is that the pressure exerted by one molecule on a very tiny cylinder with a movable piston, that force is just the mass of the molecule times the velocity squared divided by the volume of the cylinder. And this quantity mv squared is should be familiar to you. It's just twice the kinetic energy that the molecule possesses. So you've got this very nice relationship that relates the pressure in terms of the kinetic energy of the molecule and the volume of the cylinder that the molecule is confined in, right? And this pressure, of course, is what you measure experimentally. This volume is what you measure experimentally. It's very hard to measure the kinetic energy of this gas atom experimentally, but if you can measure the pressure and the volume and multiply them together, this relationship tells you what the kinetic energy is in a very straightforward fashion. So I think the next point of the argument is, let's extend the argument now to a finite size cylinder. So what we're going to do is we're going to take that long skinny cylinder that was in the y direction, we're going to rotate it. So now the piston is going to be free to move in the x direction. Now our piston is going to have a three-dimensional geometry associated with it. The volume of the cylinder is no longer going to be this one-dimensional tube. It's actually going to be a cylinder, a finite cross-sectional area A. And the point I'll make is that the arguments that we've already constructed pretty much go straight through, because in this case, the only change in the velocity along the direction of motion of the piston v sub x, right? The only change in the velocity component along that direction of piston motion is the velocity v sub x. So the y and the z component of the velocity remain fixed as the molecule interacts or bounces off the piston, but it's the x value or the x component of the velocity that changes sign. It's just like this argument here, right? That there was only the y component of the velocity here that changed sign on collision. When we extend the argument to a piston a real piston, you know, a piston that you find in the real world, it's only the x component of velocity that changes sign. And that just simply means all the argument that the algebra that we've used in the previous few slides just comes straight through. The only difference is we're now looking at velocities in x rather than velocities in y. So the next question is, what happens if you start to put n molecules in this cylinder, and you ask what's the net pressure exerted on the piston with n non-interacting molecules. Each molecule has the same mass, but there could be different velocities for each gas atom in the piston. And so we have to subscript the velocity in the x direction by an index I, which indicates which particle is moving and what velocity that particular particle has. So if you want to calculate the total pressure exerted by these n molecules, you have to sum up the individual pressures exerted by each molecule. And what we just showed is that those individual pressures are just the mass times the velocity squared in the direction that the piston moves in, divided by the volume V of the cylinder, right? That's the result that we've already shown on the previous slide. And what we're left with is evaluating this sum of the velocity squareds in the x direction over all the gas atoms in the cylinder. And it's not clear how you would calculate that, right? Because in principle you would have to measure the velocity of each gas atom in the x direction if you wanted to evaluate this sum. And maybe you can do that if you've got 10 or 100 particles, but when you start to have 10 to the 19th gas atoms per cubic centimeter, this becomes intractable, this sum. So the way you solve this problem is you convert this sum into an average, right? And you do that by multiplying and dividing by n the number of gas atoms in the cylinder. This quantity in red brackets now is basically an average value of a large number of particles, and it's the velocity squared in the x direction, averaged over all the particles n in the system. And what we can do is we can represent that by some number, v sub x squared with the subscript average on it. And this is a quantity that represents this average value. It's a quantity that we can't directly calculate, but it's very well defined because n here is a very large number, and as n gets very large, right, the average value of a collection of velocities, a collection of gas atoms, all with a different velocity, let's say in the x direction, that average value becomes extremely well defined as n becomes large. So what this realization allows you to do is it then allows you to write an expression for the pressure times the volume of the gas in terms of the number of molecules n contained in the cylinder times the mass m times this average velocity v sub x squared. And of course this m times v sub x squared, that's directly related to kinetic energy that the particle has when it's moving in the x direction. So far this discussion only contains mention of the x direction. What we like to do is we like to compare this result to the ideal gas law, and that's what I do in this first slide right here. So for the ideal gas law, we know that pressure times volume is equal to the number of molecules n times Boltzmann's constant K sub b times the temperature T in absolute units in Kelvin degrees. And what this allows you to do is this allows you to define what this average velocity in the x direction is squared, because the n's cancel out, and now this quantity T, which is a thermodynamic variable, right? It's very clear that this quantity T is related to the average kinetic energy that these gas atoms have, right? So that allows us to identify operationally what the temperature of the gas is. The argument goes further because you have to realize that this average value of the velocity squared really is the average value of the x component, the y component, and the z component, right? And so rather than measure the x, the y, and the z component, maybe it's easier to think about the average velocity squared according to this condition. You have to realize that in principle, there's no difference between the x, the y, and the z direction inside this cylinder. So if you're a gas molecule, you don't really care whether you're moving in x, y, or z. They're all equivalent. That allows you to set up this equality that says that the average value of the velocity squared in the x direction has got to be equal to the average value of the velocity squared in the y, has got to be equal to the average velocity squared in the z direction. And that can then simply be used to rewrite the average velocity squared in terms of the average velocity, let's say, in the x direction. This factor of 3 just comes about because we've got 3 degrees of freedom. We've got x, y, and z that the molecule can move in. So the upshot of that realization is that you can rewrite the ideal gas law in terms of the average velocity squared of the gas atoms, not the average velocity in the x direction of the gas atoms. The price you pay for that is this factor of 3 that comes in right here, right? And at the end of the day, you're left with this very nice relationship that says that the average velocity of the kinetic energy, 1/2 m v squared average, is just equal to 3/2 kT, right? And this is a very important theorem. It's referred to as the equipartition theorem. And it shows up all over. It shows up in biology, chemistry, physics, all different branches of science and engineering. So what we can do is we can take these results, and I just summarized possibly the three most important results that we've derived in this lecture. We've got now an expression for the total kinetic energy of the gas, and that total kinetic energy of the gas is related to the kinetic energy of each gas atom. We got N molecules or N atoms in the cylinder, so that gives us the total kinetic energy, and it turns out that's just equal to 3/2 Nk times T. The average velocity squared of the gas atoms can be gotten from this formula, and it turns out that's just 3kT over m, where m is the mass of the gas atom. And what we can then do is we can define the RMS value, the root mean square value, which is the square root of the average value of the velocity squared, and we get this result 3kT over m square root. If you're used to dealing with moles and molar volumes and moles in terms of the actual quantities N, then these formulas for velocity are often rewritten in terms of the universal gas constant R. So here, capital M is the molar mass compared to the mass of the individual atom or molecule. So to set up the next lecture, how can we do better to characterize these gas of N atoms if they're in an equilibrium at some temperature T? Well, the answer is you might want to try to measure the average position and velocity of each gas atom. You might want to construct a table, for instance, that lists the position, the velocity, and the energy of each gas atom in that cylinder. That might be your first approach on how to characterize this gas in more detail. The trouble is you have to make a table like this for every time that you care to think about, right? Because these gas atoms are constantly colliding with the walls and with each other. So these positions and velocities and energies are constantly changing. So it quickly becomes intractable. Maybe you can make a table like this for 10 or 100 gas atoms. But when you start to get 10 to the 19th to 10 to the 20th gas atoms per cubic centimeter, such a table is impractical. Historically, the way the problem has been discussed is in terms of a probability distribution. So what we're going to show in the next lecture is we're going to show that there's a distribution that allows you to calculate the probability that a gas atom has a particular velocity v when it's contained in a volume that's held at an equilibrium temperature T. And this probability distribution is known as the Maxwell-Boltzmann probability distribution function, and that's going to be the topic of our next lecture. So it's going to, if this probability distribution function is derived correctly, right, it's going to recover all the results that we learned in this lecture by looking at the way these individual gas atoms move around inside of a cylinder. So this is kind of a review of kinetic theory of gases. You may have seen it once before. If not, you know, the main point of the lecture is to get you to appreciate the overall idea that you can apply these simple kinematic equations to derive explicit expressions for things like pressure and temperature for an ideal gas. So we'll see you in the next lecture.